Hello and welcome to this presentation. My name is Audrius Zidonis. I am a lead mechanical engineer at Typhon Treatment Systems, and today I would like to present you a case study of numerically modeling a performance of a large-scale UV LED reactor. This study was done together with my colleague Dr. Olivier Autan and our research partners at Lancaster University, Mr. Janil Shah and Professor George Agidis. So here's a summary of the validated range of the reactor that's used for this case study. As you can see, it can go down to 70% UVTs and up to 500 cubic meters per hour flow rate. The validation was done in conjunction with the TZW and Carollo engineers. Now, the reactor design consists of three key modules: a UV reactor module, which has the UV LEDs, a swirl module, which provides the flow conditions, optimized for the reactor, and the heat exchanger that provides passive liquid cooling to our LEDs, so we don't require any external chiller or AC to cool the LEDs down. The reactor itself is a 300 millimeters diameter, completely open inside a quartz tube, so the flow is going through a full bore 300 millimeters diameter of this quartz, and the LEDs are fitted on the side outside of the reactor, and they're paired with the reflectors. So what the reflectors do, they form a beam of light by concentrating the light towards the center of the reactor, and as we have 20 of those LEDs per ring, and then the rings are alternated, that provides a evenly distributed UV intensity inside of our reactor. Now, in addition to the optical design, the hydraulics matter as well. So the reactor itself is very simple in terms of hydraulics. It's just a straight tube, but the swirl module, it has this swirl-inducing static vanes, so they produce the swirl for the reactor to improve the mixing and to improve the dose distribution. We also have, as I mentioned before, the heat exchanger module. Now, the heat exchanger could be fitted out, at the outlet of the reactor, or at the inlet, or somewhere a bit further from the reactor. But for the validation configuration, we have decided to install it right upstream of our swirl module, anticipating that these would be the worst flow conditions that the reactor might see. So, this would open the possibility to do other modular site installations, and making sure that the REDs there are the same or higher than what was seen at the validation. And on the right hand side, you can see the actual installation as it was done at TZW. So we have 1,000 LEDs fitted outside of the quartz tube, and each LED is paired with a reflector, which makes the modeling a bit tricky. We do need to do proper ray tracing to make sure that we capture the shape of the light beam that's leaving the LED correctly, and trying to model 1,000 LEDs at the same time is computationally expensive task. So what we do is we actually take a single LED and a reflector positioned on the quartz tube, and with a defined UVT of water inside of it, and we do the ray tracing. The ray tracing is done in a Zemax Optics Studio, and what you can see here is just a fraction of the rays. If we were to show you all the rays that are tracked, you would simply see a blue triangle here, and then the data from the rays is converted into the intensity data on a 3D cuboid detectors, also known as voxels. Again, those voxels here are shown much larger for clarity than what they actually are in the model. And over here you can see again some randomly selected rays, and you can see how they're being reflected and shaped into the beam for our reactor. So once we have that 3D data, we can then build the 3D fluence, or the 3D light intensity distribution data of our reactor. And we do that in MATLAB. So if we look down the reactor, so we're looking perpendicular to the quartz, or perpendicular to the flow, looking at a single LED, you can see that the intensity is dropping as you're traveling towards the center of the reactor, and it might appear that there's not much intensity left by the time it reaches the center of the reactor. But because we have 20 of those LEDs outside the ring, we get a multiplying effect. And in fact, you even have a slight hotspot in the center of the reactor. And to make sure that we don't have these cold spots close to the periphery, what we do is we do the alternating rings, so they cover each other up, and we get really good light intensity distribution inside of our reactor. So this is a model result, but if we look at the actual photo down the reactor, we see a very similar distribution. So once we have that optical data, we go to CFD modeling. Now that's a fairly standard exercise. You take the flow domain geometry, take the hydraulics, you convert that into the mesh. So just discretizing the geometry, and then we run the simulation. The simulation is performed in ANSYS CFX package. In our case, the flow is fully turbulent. We don't have any rotating parts, so the flow conditions can be assumed to be statistically steady state, which means that the RANS turbulence models are appropriate. Now, the most popular RANS model is K epsilon, but it fails to predict flow separation. So in our case, we use K omega shear stress transport turbulence model just to have a bit more accuracy on what we do. And once we run that model, we can see how the flow is swirling inside of our reactor. And as you can see, the swirl isn't concentric, which is good. We want to have some lateral mixing just to diffuse that hot center that we've seen in the intensity UV intensity graphs. But to be able to quantify, we instead of looking at the velocity vectors, we have to trace some of the trajectories. So on the left hand side, you can see 10 trajectories. Those are traceable by the eye, but for the actual quantification, we do need to export a lot of them, and in our case, we do export 5,000 trajectories for the reactor. And then we integrate those flow trajectory data with the light intensity distribution data, and we can then get to the result of UV dose distribution in our reactor. So you can, one way of presenting it is by histograms, but I personally prefer the probability distribution. So in this example, we can see that 50% of the flow is getting 33 to 40 millijoules dosage, and then the rest of the flow is getting in the range of 50 to 70. We can convert that data into log reduction for a chosen organism or into RED. Also, we can get the mathematical average of the dose, which we can then use to estimate the reactor efficiency. So in this case, for this particular data point, we can see that if we use MS2 as a challenge organism, we get about 90% reactor efficiency. If we look at the reactor efficiencies over the entire range of the operation, we can see that in terms of the flow rates, the efficiency is consistent. Going from 30 to 500 cubic meters, the data points are really tied together. But in terms of the UVTs, we have a bit more variation. So you can see that for 80 to 90% UVTs, we have a peak, and these data points are above 90% reactor efficiencies, but it can drop down to 70% if we go for 70% UVT. Now I have to emphasize that this performance curve is for this particular reactor design that we're choosing for this case study. and we have chosen the peak to be here because it's a drinking water application. So we are looking at more of a higher UVTs, and it's really easy to deliver the dose at UVTs that are 95% or higher. It is a bit more challenging to deliver the dose in that range. That's why we want our reactor to be optimized for the most difficult condition that it's going to be regularly seeing, which then produces a flat characteristics of that reactor. And this bit we consider as an extended range of our reactor, so we don't expect it to be operating in that range very often or in many installations at all. But in the validation process, we did validate it down to that, just so we can offer the validated range for this reactor. For actually, if we were to optimize, or if we were to design a reactor that's going to be permanently sitting for those UVTs, we can do that by selecting different number of LEDs per ring, or changing the reflector design, or adjusting the reactor diameter, and then we would have moved the peak over here. But as I said, for this case study, I'm only interested in this particular reactor design. Another application of the modeling is to make sure that we are delivering the same dose as we install the reactor. So in this case study, we had a very limited space inside of a filter gallery. As you can see, that there are a lot of components already around. So we have moved the heat exchanger downstream in its vertical position, just to be able to utilize the space that was available vertically, and to reduce the flange-to-flange distance to a minimum. Now, having done that, we had to confirm that this doesn't affect the dose delivery in any bad way. So we have run the model in the conditions that this reactor is going to see in that particular site, which is 4 log cryptosporidium inactivation, and the flow rates per the line was up to 250 cubic meters per hour. We do a comparison of water treatment plant installation to the validation installation, and indeed we can see that the dose is same or greater, which is good, and also reassures that the validation installation that we have decided on was actually the most conservative one. So it opens us the ability to do quite flexible installation in the field. And just to summarize this presentation, I hope I have explained why modeling of a large UV LED system with 1000 LED sources may be quite challenging, and what methodology can be used to go about it, and where this modeling can be used. And as a next steps, we're planning to assess this modeling against the experimental results from this validation that we've recently performed, and also we're looking to calibrate the model per the innovative approaches suggestions, just to improve the modeling capacities that we have in-house. So thank you everyone for your attention, and have a good day. Goodbye.